Swayam Prabha. Digital India. Educated India.
So now we're going to move to population-based methods called evolutionary method is one way, evolutionary optimization. The evolution what comes from natural evolution, not nothing else. So I'm going to introduce you to this, show you the working principles, genetic algorithms. You may have heard, many of you, that's one of the evolutionary algorithms, but there are many exist today. Other day I was counting, it's crossed 100. Okay, so many, we're not going to cover all of them. 2 case studies, I'm not sure if I kept both, but there will be a lot of case studies with multi-objective that's coming, how to handle constraints and some mathematical underpinnings. Okay, so what's the motivation? We see in nature, as I said, lots of examples that look optimal. Okay, that satisfies our scientific ideas. And Darwin talked about this guided evolution, the survival of the fittest concept. In a population-based method, if you have lots of population members and they are evaluated based on some kind of fitness measure, the ones that are less fit is going to die and give space for more fit individuals. Now you need a creation mechanism from the current population to replenish the ones that will die. So that's the process iteratively over millions of years. Millions of iterations have taken place to what we are today, and it's still a process that's continuing. So if we just keep it over there, it's not coming very well, I don't know. Let's keep that animation. Now there is some precision issue, I think, with what I see here, and it's not very crisp, but anyway, I think I will see how some of the simulations will come up. But here is an overall sketch of an evolutionary algorithm. So you see that first you need to do is, so this was first of all suggested way back in 1962 by Professor John Holland of University of Michigan. He died about 3 years ago, but he did a lot of other things besides this. What I'm presenting you here was in very premature stage when he wrote a book in 1975 talking about these methods, and then many of his students, PhD students, one after the other, took the idea and matured it. And then of course I joined in this field in 87, almost at the beginning. The first conference started in 85, so I just missed one of the conferences, but since then I have been very much involved. A lot of my colleagues came and went. They thought this is not going anywhere, but I kind of stuck to it because I found there's something here that's very unique and novel. And as you will see that we've contributed in a very major way in some basic ideas. So many of my methods are now default used in commercial softwares as well as by other people. So staying long time in a field is very essential. You are like all young and trying to build your career. Do not switch around that much, because I see a lot of young people who just all over the place. That way you are not going deep into any field. When you are at my age, you need to have something behind you to say, here is the guy we want to call if we do this. Okay, you may not be called for everything, but if somebody is thinking of that, then you are the guy. So that let's keep it this way. And then if you spend like 30 plus years, you know about the 10,000 hours thing, right? You heard of that. Yeah, so to master any field, you need to spend at least 10,000 hours. So in your PhD, count how many hours you have spent. If you're not spent close to 10,000, don't go to your supervisor and say, I want to graduate. Okay, because you don't have the expertise. So count every day. If you want to finish in 3 years, count how many hours a day you have to work. Because that really, if you want to learn piano, you have to spend 10,000 hours. If you want to do any sports, you can become an expert. Of course, your physics should allow it, but minimum time you have to spend is 10,000 hours. That's kind of, that book is very nice, talks about various different fields, cooking to everything. And I find that true with my PhD students, with my life as well, is what I have seen. So it's a good number to go by with, and you can give the account to your PhD supervisor that, see, I spent 10,000 hours. And Professor Dev told us that that's enough. So, yeah, and show him the book. Okay, so anyway, so that's something that's kind of now matured, and we believe that this is what the algorithm, but still evolving, that you could do. So you start with representing your solution. If it's a continuous variables, there is nothing to represent, just every variable is a variable. But sometimes you may decide to do a binary coded GA versus a real coded genetic algorithm. Then you need to think of a binary coding for every real number, which I'm going to show you soon. A iteration counter, to be fancy, we call generation, put to 0. Then initialize your population. Let's say these are my initial populations. I just got 7 of them. Usually we put an even number. Sometimes we do multiples of 4. There is an advantage to do multiple of 4. I'm going to tell you. So initialize the population, evaluate each of them, means compute F, compute G's and all that. While you are not terminating, so you need a termination condition. Take that population and select the good ones using survival of the fittest concept, right? We will show you. There is a tournament selection usually we do, basically pairwise selection, and you get what is known as a mating pool. It could be these 4 solutions are better than these 3, so there will be some of them will have duplicates. Okay, this is almost the same, it's exactly the same size as PT. And then you take that good solutions and apply a couple of operators. It could be more operators as well, and there you could put customized operators. Recombination and mutation, as we call it. Recombination is an operator where you take, this is a binary coded GA, every variable, so this is variable number 1 coded in 5 strings. This is variable number 2 coded in 5 strings. I'm going to show you how the coding works. And then you consider the whole thing as one string. And then you choose a cross site, as you see here by a line, this line here. This could have been another line. And you swap the information on this side, on the right side of the line, and you get 2 new strings. So 0, 1, 0 get attached to this, and I get a new one. And this one get attached to that, and I get a new one. So these are children, okay, and these are called parents. Then this could be these open circles are the children when you compute their x1, x2 values, and now you evaluate them. It's not necessary always you get better, okay, but you evaluate them. And then what you do, take these solutions. Okay, I should tell you about one operator called PC, crossover probability, which is like, you don't do cross to every pair like this from the population P-T. You do PC percentage of them. So if PC is 0.9, 90% of the pairs will be crossed, and 10% will just go like this without any cross. Okay. Then you come to mutation, you take one of these and flip one of the 1s to a 0 or 0 to a 1 at random. Usually you use a probability called PM, which is 1 over, almost like 1 over L, where L is the number of strings. So almost 1 bit, on an average, 1 bit per string gets mutated. So it's a very small change you are making. It's called a perturbation operator. This is more of the main operator. You can take 2 strings, the good part of both the strings can get attached into one. So that kind of recombination ability this algorithm has. So at the end you get the same number of children as the original parent size, but they are now different because you did crossover, recombination and mutation. Evaluate them, children population, combine parent and children into one, and then decide who is going to survive. It could be that 2 from the parent survives and 5 from the new offspring survived, and we have the total 7. That's your PT plus 1, increment the counter, go into this loop until you terminate. So there was a competition one time in one of our annual conferences. You can use any computer language. Who can come up with the minimum line code for implementing a simple GA like this? Can you guess which language? Which language at least? It was MATLAB with 19 lines of code, and it's a working code because the evaluators were actually using them to test a lot of problems. Okay, so the reason for me to tell this is it's a very simple code. Okay, the algorithm is very, very simple. You can see it's just a do loop. Okay, now back in 1995, Gunther Rudolph from University of Dortmund in Germany, he's still active, he came up with an asymptotic convergence proof of these algorithms. For him, recombination is not important. For him, mutation is important, and the selection. And there is another thing, this survivor operator, that is important. So he said, if you have these and you keep running this algorithm, eventually you are going to reach the global minima of any function. Does it violate NFL? He says any function, give you the global minima. But for the NFL, you needed a fixed number of time, okay, which means fixed number of iterations, fixed number of function evaluations. This is an asymptotic proof. Gunter's theory says, oh, if you give me a finite time, whether this algorithm will reach the minima, I cannot tell you. But if you give infinite time, it will eventually get there. That kind of asymptotic proof is also important than not having any proof. So at the back of your mind, you always know what you are doing is taking you in the right direction. But it could be slow sometimes, not enough speed that you expected, but it always works in the direction of the optima. So to me, it's not important, this proof, because I'm solving a lot of practical problems. They cannot wait infinite time or millions of years. They need a solution today or tomorrow. Then this proof is not important to me. So I don't care about the proof and what are the assumptions to get to the proof. I only tell it to you because many times people come and say, is there any proof of this? Because you're doing a lot of random stuff. Does it work? And then I say, yes, there is a proof that says it works. Okay, so we need to you have to take a semester long course to understand some of these details of how this proof works and everything. But here I'm giving you just a brush up of the main ideas and main theories. So let's take an example. Let's say it's a binary coded GA we're going to use that John Holland came up with. So I'm going to do that CAN problem I introduced to you. Diameter, height are the two variables. But instead of using these real numbers, D and H, I'm going to code them in binary strings. So here is D coded to a number. Here is H coded to a number. So this is a binary string, most significant, least significant. So when I decode, what will be the value? 0 plus 2 plus, sorry, these are all 0. So this gives you 8. So you're right, 8, and this will be 10. So let's say I'm going to map it between 0 to 31 for now. So I will be just getting 8, because if you have all ones, it will be 31, all zeros, it will be 0, right? And I'll get integer values. So you see, binary coded GA naturally does integer programming or any discrete programming. You don't have to use branch and bound or any of those. Okay, now if you add one more bit here, you can get 64 values. So you can actually have 0.5s, right? If you do 2, you can have 0.25. So you can add the number of beats for every variable and you can get lots of precision. Okay, so first thing for you to do is this, decode these two numbers D and H, and then plug in here. This is the circumferential area and these are the two leads area. So this is the total area you want to minimize. And then there is a volume, that the volume inside, which is this, has to be at least V, which is given, let's say 300 milliliter. So now solve and give me the result. Of course, D and H has to be greater than or equal to 0. Both D greater than 0, H greater than 0. It cannot be negative. Okay, so that's the problem. I'm not going to solve it here. I'm just going to show you how one iteration of the GA will work. So first of all, for any x that is coded between A and B, the x goes between A and B, here is the mapping. You get the decoded value like 8, and if B is 10, A is 2, then L, if you choose 5 bits, then this gives you the x, corresponding x, and they will all have uniform distribution. For example, if your S is all zeros, your this is 0, decoded value is 0 for that. So whole term drops and x is equal to A, you get the lower bound. If you have all ones, decoded value is 2 to the L minus 1. So in this case 31, 2 to the 5 minus 1. This gets cancelled, A gets cancelled, you have x equal to B. So all zeros give you A, all ones give you B. And any other string in between will have a decoded value in between 0 and 2 to the L minus 1, and you will get something in between A and B. Does that make sense? So by increasing L, you can have more and more precision. Here is an example. If lower bound is 2, upper bound is 10, L equal to 5, then here is my mapping. And then if I take an arbitrary string, decoded value is 11, 1 plus 2, 3, 3 plus 8, 11. So I put 11 here and I get the value which is 4.8387. Right? So that's my x vector. Now I plug it into my formula for objective function and constraint. So this is how binary coded GAs work. So the precision here is this much, because every time you change the S, you can expect to have one increase in the decoded value. So this much will increase from here to get the next value. So between two consecutive values, you have 8 by 31. Or in general, if you want to see that I want 2 decimal places of accuracy, then I want to find what L is going to make that happen. So I have to go back to this formula. This has to be, so B minus A over 2 to the L minus 1 has to be at least equal to 0.01 if I need 2 decimal places. You can solve this to get L. What should be the minimum value of L? That's what I do here, and it says 10. So I need at least 10 bits for X to get 2 decimal places of gap between the 2 consecutive values. This is how you decide how many bits are needed. Okay, an example to that CAN problem. So let's say I've decided to have 6 members in my population, randomly created bits with 5 bits for D and 5 bits for H, and I code it back and show you actually how they look. And these values are the objective function values. Okay, if the volume inside is not at least 300 milliliter, I add something, because this one doesn't have 300, this one doesn't have 300 inside. I have added the remaining part. So this is 28 milliliter short of 300, this is 35 millimeter short of 300. These ones are more than 300 or equal to 300, so I don't add anything. So it's like that penalty function I showed you. So my overall function is a penalty function. This is nothing added, so 23, 30, 24, 26, this one will be 39, this one will be 44. Okay, so that's my initialization, my initial population. I want to apply one tournament selection. So what happened in tournament selection? I'm going to pick the good ones. One way to do this would be, I delete the bad ones, maybe the bad 3, which is these 3, and I make 2 copies of the best ones. We don't do that in GA. We don't do anything deterministic, because as soon as you give me a deterministic algorithm, its application gets limited. There will be some problems where this determinism will not work. So we like to keep some probability event, a stochastic event. So we don't do it this way. How do we do? Here, there is a concept of tournament size. In this case, I am keeping with size equal to 2. What does that mean? I shuffle all my 6 members which are here. This is my PT, right? And this is my P dash T, if you remember that mating pool. But yeah, how do we get this? I'm showing from here to how do I get that. So these 6 members, I shuffle them like you shuffle a pack of cards. You don't know where is what. You shuffle them. Now you take the first 2 and apply a tournament like you play in games. Tournament is based on the objective values. Since you are minimizing, we pick up the one with the smaller value. So here 23 is smaller, I keep it here. Then I take the next 2, 24 versus 39, 24 is better, I put it here. 26 versus 44, 26 wins. And I'm done with the end. Because I'm doing pairwise, I will have half the size filled up here. To fill the other half, I take another shuffle of this population and do it here and repeat the process. And I pick up the other half. This is how I get my P dash T. And this is exactly what I have here. So let's observe what happened in this process. What's the best one here? 23. How many copies do I have here? 1 and 2. Is it a fluke? Because I have done, if I randomly shuffle these or shuffle these, I may have a different outcome. But will I ever have 1 copy of 23 or 3 copies of 23? How many copies of 23 will be here? Doesn't matter how I shuffle them. Anyone? Why? 2 times we are doing this. Both times 23 is going to win, because no matter with what you compare 23 with, it's going to win because it's the best. Correct? Everyone agrees? So 23, I have a deterministic event. It will always have 2 copies in the mating pool. How about the worst one, 44? I don't have a copy. Is it always going to happen? Yes, because it's the worst one. It's going to lose here, it's going to lose here. Both tournaments, no matter with what you compare it with. Okay, these two are deterministic event. Let's look at the second best, 24. How many copies do I have? 2. Is it always going to happen? No. Only time if 24 is compared with the best, it's going to lose. But what's the probability here of that's happening? Yeah, so one is compared with the other, so it is 1 over the population size, right? So whether I compare this with this, or maybe you can do a little finer calculation here, and it's probably 1 over n minus 1. So if I have 6 is 1 over 5, 20% chance that it's going to happen. But usually my population sizes are 50, 100. In that case, my probability of that's happening is very, very small. So you will probably see the second best will also have 2 copies in most occasions. Third best may also have 2 copies. At some point in the intermediate part of the population, you are going to have 1 copy, because one time it's going to win, one time it's going to lose. And then when you go down to the list, you're going to have 0 copies, either 1 copy or 0 copy. But these two extreme events are always deterministic. So it's a very nice way of mixing up determinism and stochasticity part of it, so that you are getting what you want. Our goal here is to have more copies for the good ones, less copies for the bad ones. That's the Darwin survival of the fittest simulation here. It's called the tournament selection with tournament size 2. If I want to have the best one to have 3 copies, how do I change this algorithm? So now the 23, I want 3 copies here. How do I do it? Yes, but how do I implement with tournament size 3?
Out of 3 we will choose.
Yeah. So I'm going to take these 3 and choose the best. Then these 3, choose the best. So I have to do now 3 times. And every time the best one is going to win. Every time the worst one is going to lose. And then others will have 3 copies, 2 copies, or 1 copy, or 0 copy. Right? So this is how we can increase the tournament size. But you see, when I go from 2 to 3, the best now out of 6 will have 3 copies. So I will lose my diversity here pretty soon. They are all the same. Because imagine now, from here I will pick any 2 and do crossover. And if there are more of 23, good chance that same 2 solutions are chosen from recombination. Then any recombination I do is not changing, because there is no diversity left in them. So it's not a good idea to have too many tournament sizes. Okay, maybe one smart question. What if I want 2.5? What shall I do? Not 2, not 3, but 2.5. Or let's talk about 1.5. 2 is already too high for me. What does it mean, 1.5 copies? That means if I repeat this, it's a stochastic event, repeat this many times and count how many times I've got 23 over 10 runs and divide by 10. And I get 1.5. How do I achieve that? So sometimes I get 1, sometimes I get 2, so that the average is 1.5. Yeah, how? When I decide which is better, I do tournament size 2, but which is better, I use with the probability 0.75. This is better, 0.25, this is still better, 30 is better. So when you do that, I'm not always taking 23 when these are compared with that. 75% of the time I'm taking 23. You will observe that on an average you will have 75, because you are doing 2 times. So 0.75 times 2, which is 1.5 copies you are going to get. Okay, so we implement sometimes this. What happens is when you have a flexibility like this in your algorithm, and you are trying to solve a problem for the first time, which is very complex, you start with the standard tournament size of 2. And you observe that you are losing diversity very soon, because in those problems, maybe it's very difficult to get a good solution created out of a recombination and mutation operator. So your best solution is getting multiplied many times. You are losing. 2 places to concentrate. One is reduce the selection pressure from 2 down to 1.6, maybe 1.5, and come up with a different recombination and mutation operator that has more ability to create better solutions. That sometimes is difficult to do. You need to have a good understanding of the problem. But these are the 2 places you will look at. Okay, so what is a recombination operator? Then I already mentioned to you, and I already talked to you about PC, so I don't have to do it here. Mutation also I talked to you about. Yeah, so with the selection, recombination, and mutation, you basically have the very good algorithm. In the absence of any one of them, it's not a very good method. Yeah.
So okay, we don't know the right TSR.
Yes.
So in that case, should we have to see how the algorithm is progressing between?
Right. So this is another totally subfield. It's called hyperparameter optimization. A lot of people in Europe is working on this. So you have a basic algorithm, and that goes with point-based methods also. Every algorithm has some parameter, algorithmic parameter. What is the algorithmic parameter for Mendler-Mead search? We talked about the expansion. I told you 50%. You can do 60%. You can do 20%. That's a parameter. When you shrink again, so there are a few parameters every algorithm has, and authors have already defined it for you. They did it on many problems and figured out this worked the best, but that doesn't mean you can change them. Same here, you see this PC, PM, population size, and now we are introducing this TS also. So these are my algorithmic parameters. There are some standard values we can use. First time I'm solving a problem, I use the standard ones. I go all the way to the end and see what values, what results I get. If I'm not happy with the performance, then I fiddle with them, parameters, and see when I'm getting the best. Either you can manually do, but if you have 10 parameters, you need to do very systematically. But there are algorithms to do hyperparameter optimization. So it's a nested optimization where you change these parameters. You have now a setting, and you then see how your algorithm is done. A fitness function goes to how good is these parameters, and then another GA is running on them to work on the parameter space. So eventually you get to a good parameter setting and also good result on your problem. So these are called hyperparameter optimization. There are a lot of methods that like that. Okay. Yeah, I don't know, they're not coming well here. Here also they're not really coming very well. But when it comes around, you can see that it starts with lots of points in this space, and there is an optima. So very quickly this kind of GA figures out where the feasible region is and where the good things are, right about there, and then it's doing kind of creeping. So you can actually stop GA right about here, okay, and then use a hill climber to climb up the hill. Yeah.
Maybe we can try to see if the animations can come better. Is that okay? He says if we go back to the old format.
Okay, we'll leave it for now, but we'll fix it so that from tomorrow we could do this. Yeah. All right. Thank you. All right. So there are a lot of differences with classical method. First of all, in binary coded GA, we're dealing with a binary coding. Then we have a population, and the classical point methods have only point. And there is a concept of implicit parallelism that already comes in with these methods, because you are parallelly searching different parts of the search space. So that's the implicit parallelism part. And then we are using probabilistic operators, so it's very difficult to get stuck or kind of married to an algorithm in some sense. We never talked about gradient so far, so it doesn't need any gradient, but if you have gradient, we can motivate our operators based on gradients, which you have done in a couple of problems with industries where the gradients are available. And ideal for parallel computation. You can evaluate your offspring populations among multiple processes. That's the very easy way to do distributed computing. Yeah, let me skip all that. Show you that this has been adopted in many different real world problem solving problems. Here is one on the left side is the Japan Shinkansen, the blue bullet train. Okay, first time they did it in 2007. Before that, they used this point-based method, conjugate gradient method is what they have used. And then 2007, they wanted to change the whole design, because their goal was, if you think of Japan, most people live in the coastal area because the middle part is very hilly, nobody lives there. So these trains actually go very fast through these highly populated areas. Okay, and so they made tunnels, and so when the train comes, the air goes with it, hits the tunnel wall, comes back, and then interferes with the upcoming winds, and it creates a lot of reverberations. So if you have a house like close to that tunnel, do not have enough life if you have not taken care of these things. Okay, a lot of vibration takes place. So the cost is not important there. Their goal was to reduce that interference. Okay, so you need to have a large nose so that it's minimized. So what will be the shape? All these parameters as you see here, that's an important decision. So they built a little optimization result to a model that goes to the wind tunnel, and it was not satisfactory. They found using conjugate gradient that previously, before 2007, they did not take care of those aspects very much. And that's the time they wanted to do. They found their previous design was not satisfactory on the wind tunnel. So then they were looking for a good algorithm. One of my collaborators from there had told them about GA. The first time they learned, they got a code, and then they ran and they found a design that passed through the wind tunnel. Now, I was fortunately present in the conference the designer was presenting, and I asked him that how did it do, and he kind of had a lot of explanation. Some curvature somewhere, it needed a global search. So the conjugate directions was getting stuck to a solution, to a constant boundary actually, which was not able to go any further from there. Since GA has this global search ability, it could find a good solutions that satisfied that. Some other person asked a question that it looks like the face of a snake if you look at it. The question to him was, because you used the evolutionary method, does it look like an animal? It was very interesting to me, that question, and I believe there may be some truth in it, because the same way snakes probably have evolved, right? This recombination, mutation kind of thing, but what fitness function nature uses, we don't know, right? And it's probably not single objective. There are so many other things, but it's an interesting thought that these shapes kind of coming out to be like this. But do snakes go at that high speed? That reverberation is the main thing. I don't know. So there is a truth in it, but I don't know how to connect it. But anyway, so since then, 2007 onwards, they every other year they modify. They are always using GA. Okay. Same story with the Kone's, Kone, you may have heard the elevator system. I think it's the second highest seller of elevators in the world. These high-rise buildings have these cars going up and down. You press a button at anywhere and it records where you have, you can also go up or down, all these are recorded. Then they have come up with a GA system for controlling which car will stop where. Half a second, it records all the thing and then runs a GA in a chip. So that's the first time they did way back in 95, GA in a chip. So it's very fast, it gives the schedule. Just to show you that it does that, from their manual I got this, you see these allocating landing calls using genetic algorithms. So they've been doing it since 1995. Recently I looked at this, I don't know whether I have that plot here now. I got some curve and they compared with various other methods. They keep on improving that GA. But this is something they're doing. These are just two examples, but there are lots of other things. So where are these methods good at, or why these methods are good at? First thing is, this advantage is the population based approach, right? So you can find either one solution or multiple solutions using this. Then there is operator flexibility. You can change the operators, you can customize them according to your problem. I'm going to probably, I have to stop pretty soon, so may not be today, that example. Algorithm flexibility is there. You can do crossover first, maybe mutation second, and the selection third. You can change the algorithm, you can introduce another algorithm. All these flexibilities are there. Because it's a flexible framework, onus is on you. Who is the developer of this? You need to, like the hyperparameter optimization I said, you need to fix all of these. But at least this allows you a platform where you can change a lot of things. It's not fixed, given by Marquardt or Landler and Mead, which you cannot change. So that's the other part of it, that customization is possible, but it comes with a onus. So I always put it as second. First I try a point-based method to see if it works in a problem, and so far in my 30 plus years of working with industry, Not even once I found that I can give them a ready-made solution from an existing software. Okay, small size, yes, but it could be that most of the time the industries come to me when they have tried all of these and failed, and they may have solved many of them using classical methods, but what came to me was not possible to be solved. So I always have to then think of the evolutionary way or some hybrid way. But when you have problems where you need multiple solutions, either the problem is multimodal, that means there are multiple optima, you need to find many, or you have a multi-objective where there is this Pareto set, you need to find many solutions. So whenever you need to find many, here is a nice match. I have a population where I can store, every member can be a different optimal solution. With classical, you have to find one by one by one. That's where we beat them. Okay, that's where I think these methods are excellent. Okay, maybe I should stop with this example, one example at least. This came to me from Spain. It's the Spain's power system, power company, Endesa, they call it, Endesa, yeah. So they were going, I think this was 2008, where they were going solar in a big way. They will collect a lot of solar energy and going to distribute it to the grid. So they had total 750,000 square meter. It's a large area of solar collector. You could do maximum up to that. It could be zero as well. And then the storage capacity. So once you get that solar power, you have to store them because it's a grid system. Then you have to supply. So you could. This comes with different tank. They didn't go and tell me the details about it, but every tank can store about 8 hours of storage. So if you need 8 hours of storage you have collected, you need the second tank. That's how you get discontinuity. Because now if you get the second tank, you need to invest some money and there is a sudden loss in profit. They were trying to maximize profit here. And then another thing is auxiliary boiler power, that auxiliary way of generating power, how much of that is needed. So this only 3 variables, but I'll show you what happens. There are a lot of complications of getting to the objective function and constraints, and some of them they were not able to tell me. But on top of it, they have a black box. So this is how it is I consider. There are 3 variables you supply, and this gives you 2 things. This basically gives you one thing, the profit value. What is happening inside, I don't see. I don't have math functions. Like I showed you, f as a function of x, I don't see that. It's a code they had given me, executable. The variable bounds are there, of course, and we need to maximize this. If this value is negative, it's infeasible. If this value is positive, it's the profit, and we want to maximize this. So that's the problem. I first tried, as I said, always try point based. I have these softwares with me, LGO, Lindo. They have all these branch and bound we talked about. There are different random search methods, constraint local search, all of these. They are not good. Sometimes I get negative profit, which means infeasible. Sometimes it depends on the initial solution. I'll show you one case. If I give these 3 as my initial values, I get this much profit. Then when I run the algorithm, it gives me these values. Apparently profit has increased by a little bit. Then if I give that one, I get a completely different value. Look at these things. 3 different runs giving me 3 different solutions, but completely different values. So when you see that, your final result depends on the initial point so close that so widely, you think either there are multiple optima, every time you give an initial point, it goes to the nearest one, or your algorithm is not working. When I try the other one, they always give me the same value for some reason. So these are something I couldn't recommend. Okay. So I had to design our whole algorithm based on GA. First I did is I asked my students to see how frequently we get feasible solution and what are the function values we get. So it looks like when you take 10,000 random points, we evaluate using that executable, and we take the best out of this. One time we get this, another set of 10,000 we get that. You see the difference and the difference here, which tells me this is highly multimodal problem. Okay, so we need to handle multimodality. So I asked him, okay, let's try to understand. Let's fix 2 variables and vary one of them. So we vary one, which is the solar collector from 700,000 to 750,000, and other 2 are fixed to some value. And I look at the objective function, which is profit, you see, As I increase the solar collector, the profit increases, which is likely. So that makes sense. Apparently it's monotonic. Then when he took this part and showed me, you see the massive multimodality, so it's zigzagging all over, which means slight change here is making a big change, not a big, but a change in the profit. And this is where the classical methods are getting stuck. You start from here, it goes up and gets stuck here. You start from another place, it gets stuck another place. So you need to, if you have to solve this kind of problem, you need to see it from a 30,000 feet away, that it looks like it's increasing in that direction. Ignore the undulations. Otherwise you'll get stuck. That's the difference between local search versus global search. Okay. So we got some idea that's a massive multimodal search space. So we first use a RGA, real coded GA, which we will get to use some problem. So we solve it with population size, maximum generation 150, and it's a simple no change in the code, okay? And we get consistent close to the limit. This is the profit, and you can see that this is how the best one goes up. Here you can see the difference. This was where the best classical method solution they had, and we had got something better than what they had obtained. Okay, but I was not happy with the results, because when I run it 10 times, you can see the values almost converged, but still there are a lot of fluctuations in these numbers too. Okay, so I said no, we need to make it a little better because they don't understand what is GA. So they should run every time, they should get very similar results, right? So what we did is, after running 150 generations, we look at our population of these three variables, we look at the standard deviation of them, and along the best solution, after 150, we just go minus sigma to plus sigma and initialize our lower and upper bound. For all three variables, we do it 3 times. Run it for 50 generations and do the same thing another time, we do that. So once we do that, now we get only 0.04% difference. We got slightly better profit, and you can see now these results. They are very, very close to each other, and we got slightly better results. Sorry, that one was 0.04, but this is 0.0017%. So we improve the quality of our algorithm, okay, because we are doing few other steps to make sure we have a good search. Okay, now why is this problem I'm showing you? If you look at the optimal solution we've got, we kept the other 2 variables same as its value, only change the E, and look at the distribution of the functions. Now here is the optima. You see our algorithm has found it. But this optima is the global optima, but it's useless, because if you cannot adhere to this value, whatever is that value of E, you are down here. Slight change here, you will be down here. So we need this robustness thing that we talked about. So we went to them and said, there is a good news and a bad news. Good news is I'm giving you the global minima, global maxima, global profit, but the bad news is you need to adhere to these particular value. They said no, we cannot ensure, so give me another one. So we could give them one of these, because even if you fluctuate, you are not that bad. Okay, if I take the other variable and fix the other 2, you see discontinuity, because when you are here, if you want to have more than so much power, then you need to invest on further tanks. And then, sorry, from this way, if you invest further tanks, so your profit reduces, and then you have so this is called discontinuity in the search space, and many problems in engineering has this. So if you are taking a derivative of this kind of problems, they don't exist, right? So you need a derivative free method for it to work, but we are getting to this optima with this method anyway. And then the third variable, when I do, it hits the boundary, the upper bound, and sometimes many algorithms, if the optimal lies on the boundary, it cannot handle very well. But our methods have not much an issue. So here is an example with just 3 variables, but each of them, and it's massively multimodal problem, derivatives don't exist, but the GA seems to, without any big change, GA seems to have done fairly well in getting to the global maxima. So we talked about, I think, this example, which was small, only 3 variables, but a lot of complexities. Okay, you see the multimodality, you see one of the variables hit the upper bound, and then in other case we have discontinuities in the function. All these are commonplace in engineering problems, and you can imagine a gradient based methods. So here is the maxima, and here it's also undulation. So the classical methods will have difficulty, and I showed you with some commercial softwares how it does. Okay, it gets stuck to where you are initializing and just climbs the hill because there is a maxima there, and then it stops. If you start from another place, it will climb up the little hill and then stops. So that's what happens. They can't see these function in a far away distance, like, or in a global way, that if I go in from this point onwards towards left, I am improving my profit function, right? It always sees these details that are there. But a method like evolutionary methods with the population can ignore some of these because it's a matter of points and their function values. You are not looking at gradients or anything. Gradients looks into the details of the function. So if you have an undulation function, it captures that and it gets stuck with, it gets caught into all that. But if you're dealing with just the function values, it doesn't know what is around it, whether there is a local hill or not. It just compares two solutions. So if one is here and the other is there, this is of course better in terms of function value. So this will ignore this and come over there. So all these undulations are ignored. Do you see why this works? Yeah, but then you say that, okay, there are some direct search methods for point-based methods as well, like Nelder-Mead, and there are few other methods. Yeah, those will work, but the algorithm that are there is so deterministic and works only when certain things are met, okay? They are not very, very generic. So you can try those, and maybe some cases they will work, but my experience that as you have more and more complexity, like in this problem, they have difficulties. Obviously, even if this was smooth, when you come at this point, just at this point, you know derivative doesn't exist, right? Because it's not a continuous function. So if it's not continuous, it's not differentiable. So if you are relying on derivative at this point and you do numerical gradient computation, you will have totally wrong information, right? And then these are, unnecessary things you are trying to get from the function when you are dealing with these kind of functions. So that's really where the essence of the difference between point-based and population-based are. Okay, now not all problems are like this. So that's why we first try fmincon or a method like that. If it works, great. We'll tell our partner, use this because we tried and this works. And then we are done with the project. But if most cases, as I said, none of the projects I have done so far, I could give them a fmincon solution. Okay, but I guess the reason could be that come to me when they tried all that and then they couldn't do it. There are a lot of theories about how these evolution, but particularly genetic algorithms work, under what conditions they work. There are lots of theories because we are about, I would say, the main research in this started, I would say, early 80s. Although a lot of theses had been written, ideas were there since about middle of 60s, but it took about 20-25 years before some serious work started to happen. And we have lots of theories. We have books written on theoretical foundations of these methods, but I'm not going into the details, just I'm going to give you an overview. So Holland thought why these methods work with the binary coded GA is this concept of schema. So what is a schema? So schema, as you see here, is a similarity template, okay? So let's say I have got 4 bits with me. I have coded a variable in 4 bits. So with 4 bits, every place you can have 0 or 1. So we have total 2 times 2 times 2 times 2, or 16 different strings. And here are 16 strings, 0 to 15. When you decode all zeros, right, you get 0. And when you decode all ones, you will get 1 plus 2, 3, 3 plus 4, 7, 7 plus 8, 15, right? So that, and any other string will be decoded to a value here, okay? Now, when I say a schema like this, where it's 1 and all star, so schema actually is a combination of stars and zeros and ones. Star means I don't care what it's in here, whether it's a 0 or a 1 in my string, I don't care. So this schema means I can have 0 or 1 at the first place, 0 or 1 at the first place, 0 or 1 at the third place, sorry, second place, third place. So you have 2 times 2 times 2, 8 options. So for example, 1 0 0 1 is represented by the schema. 1 1 0 0 is also represented by the schema. As long as you have a 1 at the first place here, that string is represented by the schema. So how many strings does this schema represent? 8, right? 2 times 2 times 2. Which are these 8? These are these 8. So if you get the decoded value, when it's all 0, you have 8. And then you have 9, and you have 1 here. So from 8 to 15, these 8 strings, decoded values when you come here, they are represented by this schema. So that means this whole thing here is represented by this schema. So you see, in a search space, it's a region, not just one solution. It's a region that is represented by a schema. Every schema has at least one competitor. What's his competitor? His competitor is, instead of 1, if I have a 0. Now, which region does this represent? Is the left half. Okay? So when you have 1 at the most significant bit, it's the right half. When you have 0 at the most significant bit, you have the left half. Does that make sense? Okay, so because there are 8 of them here, 8 of them here, that together, the union of them is representing the entire search space. I could give you another schema like 1 0 star 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 star, let's say, because it's the 4 bits. Can you pinpoint which region does this represent? Now this will have 2 times 2 or 4, only 4 strings. Which are these 4 numbers? And where is this region? 1 0 star star. So 1 already tells you you would be here, right? Yeah, so this part here is 1 0 star star. What are his competitors? This one, 1 1 star star. Is that all? No, there are 2 more. 0 0 star star, 0 1 star star. Because when you have these 2, I can have 4 options with these 2. So that these are the 4 regions. Okay, same width, 4 regions are 4 different schema. When you say this one, its competitors are these. What do we mean by competitor? See, what is GA trying to do is, if GA is playing at this level with just 2 fixed bits, it's basically trying to decide, am I going to be in this region or this region or this region or that region? So that's why they're all competitors. What does that mean? I have a population, right? You have seen a population moves to another population, moves to another population. Initially, I have randomly created. So most likely, if I have 40 population size, on an average, 10 are here, 10 are here, 10 are here, and 10 are there, right? On an average, there may be 1 or 2 here and there. With few iterations, GA has to decide, do I need to be here in this region, first region? Do I need to be in the second region, third region, fourth region? If you have a function like this, which schema should have more importance? So I'm maximizing, let's say, this function over the string space or X space. So I'm maximizing means these are higher values. So which schema GA should emphasize more? 0 0 star star. Because you want all your points to be here. So initially you have equal representation in all of them. GA should migrate all of these over here to this 0 0 star star. What it means is, initially you have 1 0 0 1, all of these here, and maybe 2 more other bits here. I don't care because they are just whatever you put here is going to be in this region only. With few iterations, all of them should end up with 0 0. So 1 should vanish from the first place, 1 should vanish from the second place. Everything should have 0 and 0 at the first 2 bits. Do you agree? Then only you are here. So Holland saw that and talked about under what condition this is going to happen. So if you have too disruptive a crossover, this will probably not happen. Or if you have too high a selection pressure, this may not happen. So there are some theories of when this happens. But I'm today trying to give you an idea with the schema that this is being played as you are running selection crossover, mutation, as we talked about, all these are being decided. And each of them have their parameter. Recombination has PC, the crossover probability. Mutation has the mutation probability, PM. And the selection has the TS, the tournament size. And we talked about even being 1.5 and all that, right? So all these combinations, and we have nice papers where we clearly show that if you screw up with these parameters, even a simple linear functions GA cannot solve. And because there has to be a balance of what we call as exploration versus exploitation. This is something deep into the understanding of these, so we'll not go in this course this time. But this is exactly what's happening. Now a big question is GA playing at this level? So this is called order. How many fixed bits are there? So there are 2 fixed bits, so it's called order 2 schema. But is GA also playing this schema? So its competitor is this. What does this mean again? 0 and all star is this entire region. And its competitor is only 1, which is this entire region. So first, when you are starting your run, there is a caveat there I'm going to mention. GA is playing at this level, just 1 fixed bit. So GA has to decide the most significant bit. Shall I put more 0 or shall I put more 1? It depends on the objective function you have. In this function, what it should do? It should put more zeros, right? So this schema should have more and more copies. Okay. Once all the points from here have migrated here, have come here, then gets another split. Whether it should be 0, 0 star, because 0 is already converged. Now whether shall it be 0 and star star, or it will be 0, 1 and star star. So that game will be played. And then in this problem, they will be all 0, 0 star star. Then what's going to happen? The third place will be decided. In the third place, which you have, if I just stay there, you will be 0, 0, 0 and star, and 0, 0, 1 and star. So what is 0, 0, 0 and star? It's 0 and 1. So this thing 0, 0, 0 star, and this thing here in between is 0, 0, 1 star. So now GA is going to play between these two. Which one should win in this function? You see the highest value is here. These two have a better average fitness than these two. So this one should win. So you notice when you run a binary coded GA on this problem, first the first position becomes 0, then second position becomes 0, then third position becomes 1. Once the third position becomes 1, then you play at the string level. So now it's the question of 0, 0, 0, 0, 1, 0 or 0, 0, 1, 1. Now this one is 0, 0, 1, 0 and this one is 0, 0, 1, 1. Which one should win? 0, 0, 1, 0. So that game will be played at the end and you get the solution because now you are at the string level. Okay? Now whether this happens sequentially the way I said, it depends on the population size. If you have a small population size, how small? It depends on the complexity of the function and few other things. We have population size equations to decide that. So let's say if I have 4, I'm just giving an example. If that size is 4, then maybe GA will start with this, the lowest order, okay? And then sequentially things will happen because you don't have enough room for the game to start at this level. But if I double the population, let's say I do 8, then there are lots of copies with representative here. So there will be at least 2 copies here, 2 copies here, 2 copies and 2 copies. 2 may not be enough, but maybe if it is 16, then you have 4 copies here. And now you have enough representation in every partition here for it to happen at this order 2 level. So GA will ignore this level and will work on this. There is an advantage of working with the order 2 level is if there is something known as deception, which means when I work at this level, 1 and all star, 0 and all star, in this case, like this is better, I said, right? 0, 0, 0 star, 0 star star. This is better than 1. But at this level, the other one is better. Maybe this is better. So there are some problems like that where you can construct, looking at this, that at the lowest level, one schema is better, but at the next order level, that schema is not good. So if you follow if you already converse at 0, you can never get to the global. So of course you need a multimodality. So if I have a function that may look like this, for example, okay, this kind of a function, then you may easily think that, okay, maybe I should be in here or there because most of the representative solutions here are good. So you may find this one is better at that level if you take the average of these, and the average of this is below that, but then everything is migrated here. So now there is no recovery to come here. I'm wrong in saying that because mutation can take you always there, right? So GA doesn't have to play this perfectly like the way I said, because if this is what is expected of a GA, it's not a very good algorithm. It should repair as it's working, and there are a lot of scope of repairing that. But this kind of schema analysis gives you the understanding of why this works. Okay? I'm going to just say until here. Otherwise, I need a lot of math equations to go any further details. But I think for this class, it's enough for you to have little understanding that by partitioning the entire space, it works. This is on single variable. If you have two variables, all these are happening in both axes, and there is now two-dimensional region where the GA is converging and so on and so forth.